This is a brief tutorial about luminescence. It is meant to supplement some of the reading from the Harris textbook, chapter 17. We're familiar with absorption spectroscopy, the typical UVVis spectroscopy, and what I'd like you to do is think about that as we go along this tutorial here. In a UVVis spectrometer, you typically have a light source, and through that light source, it's typically white light or something that has all the wavelengths, and that those wavelengths are then split, separated, just like think about a raindrop splits the white light from the sun into a rainbow of colors: red, orange, yellow, green, blue. And we call that a monochromator. So out of the monochromator we get just a single wavelength. That one wavelength then goes through the sample cell, and we measure how much light comes out relative to how much light comes in. And then there would be some sort of a detector over here, and that detector is would measure the signal. We would change the wavelength, and that's where you get a UVVis spectrum. A fluorescence experiment is a little bit different, and we'll bounce back to some of the theory in just a minute, but I want to talk about the experimental design here. One of the big differences between UVVis spectroscopy and, say, fluorescence spectroscopy is right here. Notice how the detector is at a 90-degree angle from the source. So what does that mean? The source light is not going to be detected by our detector. Instead, the light that is being detected is light that is being given off from the sample itself. Okay, and that's an important point to remember, that the light that is being observed in a fluorescence experiment or a luminescence experiment is due to light being emitted from the sample, as opposed to light being absorbed by the sample in UVVis spectroscopy. Okay, notice how this this majority of this figure here is a picture of our individual sample cell. We've got light that is coming in, and we call this light the excitation light, and that light goes through our sample. And we'll come back to why this figure is split up the way it is in just a few minutes, but I want you to notice that there are a variety of regions here that we need to be aware of. The first region is this part of the sample. Let's call this a sort of a dead space, because any light that gets emitted from our sample is not going to be observed, because notice where the exit slit is. The exit slit blocks any light that's in this region here. So any light that gets absorbed or emitted in this region is going to be wasted. And it's only in this blue square, the dark blue square, where there's any light that is of any importance that comes out into our detector. Light is going to be absorbed at different amounts within this region right here. Think about Beer's law, which says the absorbance is proportional to the extinction coefficient times the path length of the light. So notice how the path length of light going from here to here, is different from the path length going from here to here. And so that is going to be also an important thing. Again, we'll come back to that in a little bit. Finally, there is, if our excitation is happening in this area here, then there's this third region where there's going to be some absorption of our light. This is going to be at a slightly different wavelength, because this is the light that is being emitted. Notice this is the excitation light, EX, and this is the emission light wavelength, EM. And so that is going to be absorbed differently as well. Again, we'll come back to this in just a few minutes, but I want to give you an idea not only of the difference between a fluorescence type experiment versus UVVis, but that there are some complications that we're going to need to keep in mind when we actually discuss this. So let's back up just a wee little bit. Actually, no. Let's take a look at what what the spectra actually look like. When we take a look at this experiment here, we see there are actually two wavelengths that we can vary. We can either keep the emission constant and vary the excitation wavelength, or we can keep the excitation constant and vary the emission wavelength. So essentially we can do two different types of experiments, and the excitation looks like so, and the emission looks like so. Okay, so there's we notice some similarities here. We see that there's a mirror image. We see 1, 2, 3, 4 peaks, 1, 2, 3, 4 peaks, and there is very close similarity, but not exact overlap between these two peaks right here. So we'll come back to this in just a minute to see see if we can explain this this figure. But first, we need to talk about what might happen to light, to a photon that gets absorbed by a sample. So this is a energy level diagram of some type of sample with a chromophore. This big dark line down here is the ground state, and we're going to start right in the middle of this figure here, where light can be absorbed, or a photon is absorbed, and we get excited into what is called an S1 or singlet excited state. What's important here is just that we've absorbed some energy, and since we're talking about electronic vibration or electronic transitions, the electron has gone from a lower orbital to a higher orbital. These individual small lines that we see, this features here, maybe these features right over here, and this large set of features here, these are all what we would call vibrational and rotational modes. We can do a variety of things, as you read a little bit earlier, to a molecule with different strengths of photons, or photons with different energies. So, photon gets absorbed, then we have a transition into an excited state, and we call this this S stands for singlet. And what can happen at this point? Well, we've got all these vibrational states. So our molecule right now is actually bouncing around at some or stretching, and as it's stretching, it's knocking into other molecules, most likely the solvent. And so what might first happen is, or most likely what happens, is the sample transfers some of that energy to the solvent, and it heats up the solvent just a very little bit. So this is radiationless. This is called radiationless transition to the lowest energy level of this singlet excited state. Now there are two things that can happen at this point. That electron can then transfer from the excited state down to a ground state, or it can go to a different type of excited state called a triplet state. If it heads down towards the ground state energy levels, then this is called an internal conversion. And then the other direction here is called an intersystem crossing. What's important for us to understand that in both of these cases, these are what we refer to as radiationless transitions. Radiationless transitions do not emit any light, and they generate heat. And that's in every one of these transitions where we see this little wiggly line. What we're talking about is a transition that just generates some heat. So, electron gets excited, generates some heat, transitions either into an S0 or T1 state, but again, it's generating an awful lot of heat. Notice how there's, even in these higher vibrational states, we get a radiationless transition down to the ground state. If we have intersystem crossing into the T1, we still have radiationless transition. One of the other options at this point, once you get to the lowest energy level of the T1, is again radiationless transition. This is an intersystem crossing. Notice going from S to T or T to S, that's called an intersystem crossing. S to S is called an internal conversion. So these are just definitions that we should know. And then we drop down again radiationless transition into the ground state. All of these processes that I've noted right now just generate an awful lot of heat. The only ones that are going to generate any sort of light are when we radiationless transition down to the ground state, and then we can go directly, the lower energy of the S1 down to the ground state, or from the triplet down to the ground state. Both of these are called luminescence. And the slight difference between fluorescence and phosphorescence is that fluorescence happens between the singlet state and the ground state, and the phosphorescence requires this intersystem crossing first to go from the triplet down to the ground state. Notice how that there are some time differences here, that the fluorescence is very fast, on the order of microseconds, sub-microseconds, down to sub-milliseconds, and phosphorescence is a little bit longer. The reason for this is based in physical chemistry, which we won't discuss in this class. But these transitions are what are called forbidden, and so the transition does not happen very frequently, and it takes a long time for that transition to happen. It is much easier for the electrons to decay through these radiationless transitions and generate heat than it is for it to generate these light through either one of the luminescence pathways. Okay, so we're going to focus on just these fluorescence pathways here. And we can see if we have vibrational states of our S1 level and the vibrational states of the the S0 level and the S1 level. In absorption spectra, so the UVVis spectrum, we're starting off with a sample in a ground state, and that then an electron gets excited into an excited state, but not only just a standard excited state, but one of the various vibration levels of the excited state. So we can go from the lowest ground state to the highest vibrational state, or on the other extreme, we could go from the lowest to the lowest. The transition on the left is going to require high energy, and the transition on the right is going to require lower energy. So we see different amounts of energy here, and those are going to correspond to different wavelengths because of the relationship between wavelength and energy. Now, notice for an emission spectrum, what we've actually done is excited our sample so that we have electrons already in an excited state, and those electrons then decay giving off energy, and drop down into the vibrational modes of the ground state. Notice how in this case here we're going from our standard, or sort of our reference wavelength, and going to the different vibrational modes, we're going up to higher and higher energies in the absorption spectrum. But notice how the dark arrows here are actually smaller, so that means in the emission spectrum we're going to lower and lower energies. Higher energies is lower wavelength, so here we would expect to see our main peak and then subsequent peaks at lower wavelengths for the vibrational energy differences. And the opposite, we would expect to see the opposite for the emission spectrum. So if we go back and take a look at our two spectra, let's look at this one here for example. We see absorption, and this is our lambda naught for absorption, and the vibrational modes would go up to higher energies. And for emission, the opposite is true. Now, this doesn't explain why there's a difference between the two lambdas here, because if we go back to our picture, notice how here we're going from ground state to the lowest energy level of the S1, and here we're going from the lowest energy level of 1 back down to the ground state. These look the same, don't they? I would agree. But what we're not considering in this case is the fact that the starting material, the starting sample, may not have the same shape. When we start from the ground state and we excite the electron into its excited state here, this is an excited state where the molecule, the atoms, are still in the same configuration as if they were down here. And that configuration is probably not an optimal configuration for the excited state, because it was an optimal configuration for the ground state. So so that requires a little bit more energy to move the electrons into that excited state with a non-optimized nuclear structure. On the other hand, when we start off with an excited molecule, that excited molecule has had time to re-optimize itself a little bit and get into a nuclear configuration that is favorable for that for the excited state. When the electron is moved, it moves down into a ground state, and just the opposite is happening. This ground state is in a nuclear configuration that is optimized for the excited state. Thus, it's going to have a slightly higher energy. Notice how these, when we consider the positions of the atoms, and how the ground state and the excited state may not have the same favorable conditions, nuclear configurations, that we can justify or we can validate the difference between the lambda naught for an absorption and the lambda naught for an emission. Okay, so let's go back and take a look at our spectrometer setup here. And we said that we're shining light onto our sample and then looking at the light that comes off at different wavelengths at a 90-degree angle in this case. That light, so that means the excitation light has to travel through some sample, some part of our sample, that is essentially wastes some energy. And then when it travels through the sample that we're interested in, we have to be careful because some of it gets absorbed very little and some of it gets absorbed a lot because it travels farther. Thirdly, we have to consider how much the the emission light is actually absorbed by the sample. When we take all of these things into consideration, we get, instead of Beer's law, which, right, if we all remember, Beer's law, which is really nice, extinction coefficient times B times C, we end up getting something a little uglier. And some of you may say a lot uglier, and I'd probably agree with you. So we've got the intensity, and this is intensity, not an absorbance. So we haven't done any log terms, so that's why we see these exponentials in here. But notice how we've got a term that's due to the path length through the first part of the cell, the part that we're interested in, and then the emission part that gets wasted in the third part. Let me go back here just to take a look. Excitation in B1, excitation in B2, those two get absorbed, and then B3, and this is we're referring to as the emission. Okay. Your book goes through how to derive this equation, and if you are mathematically inclined, you're free to look through that. But essentially, we just need to know that the emission, the fluorescence experiment is a little more complicated, or the data analysis is a little more complicated than in UVVis, due to loss of intensity in region 1, absorption in region 2, and loss of intensity in region 3. What does that do for us? Well, instead of having a nice linear calibration curve, our calibration curves look like this. We've got, at very low concentrations, we're going to have a linear region which essentially obeys a Beer's law type configuration. But then we start to get into this region here, which is called self-absorption. And it's this self-absorption region which causes nonlinearity, and it makes it difficult for us to make some, to make quantitative measurements. So, for example, let's just say, I'm just going to pick a number here. So here's this fluorescence intensity. If this is the value that we observe in our detector, it's going to be hard for us to tell whether that's due to a sample that has a concentration of 4.5 micrograms per milliliter, or if it has concentration of, say, what is that, 0.3 or 0.4 micrograms per milliliter. So it makes things a little bit more complicated, and we will have to take that into consideration when we use fluorescence as an analytical tool. And this is actually where we will start the experiment, our activity lab on Friday. So what I would like you to do is think about the concepts that were covered here, read through the luminescence section, and be prepared to do some activities involving analysis of samples, and we're going to do selenium samples, analysis of selenium samples using fluorescence spectroscopy.